Okay, let's continue with the second talk of the afternoon session. The talk is by Matteo Calisti from the University of Vienna, and he will speak about Timelike Ricci bounds for low regularity spacetimes by optimal transport.
So I want to thank the organizers for the opportunity to speak in front of you. And I will talk about this Timelike Ricci bounds for low regularity by optimal transport, which may seem a redundant name, but I will basically do the Lorentzian version of what Michael Kustiger did yesterday, so comparing distributional lower Ricci bounds with the their synthetic definitions on this Lorentzian setting. So I will briefly go on with some things about the setting and the main tools that I will need in order to define everything, and then the main result and some geometric consequences to show why it is important. And at the end, some further developments or problems. So first of all, the setting is a space-time, a smooth n-dimensional manifold with a Lorentzian metric. Our regularities of interest are C1 and C11. H will be just a Riemannian metric that induces the topology and the metric distance for the background. We will say that a curve gamma, the Lipschitz curve is G timelike or G causal regarding the sign of the norm of its velocity vector. And we say that 2 points are timelike or causally related depending if the curve is G timelike or G causal. Given 2 points, I define the time separation distance between them as the supremum of the integrals of the norm of the velocity vector, where gamma is future directed, G causal. And the maximizer, I will call the maximizers G geodesics, or just geodesics in this context. As you know, this function is lower semi-continuous and satisfies the reverse triangular inequality given any triple of points that are causally related. In this setting, given this metric C1 or C11, the quintuple given by the manifold, the metric distance induced by the Riemannian metric and the transitive relation, the timelike one, and the causal one, which is just a preorder, and the time separation function form a Lorentzian pre-length space, according to the definition of Kustinger and Simon. I will need to define what global hyperbolicity is, because it will be the standard assumption throughout all the talk. So the strong causality means that for every neighborhood of a point X, we have a smaller neighborhood V inside U, such that the G causal curves with endpoints in the smaller neighborhood V do not leave the bigger one U. And the global hyperbolicity is requiring the strong causality and the compactness of the causal diamonds, where J plus and G minus are the set of points that are causally comes after or come before the point X or Y. I will, if G is global hyperbolic, under this assumption, our Lorentzian pre-length space is causally closed, which means that the subset of the product of the causal pairs is a closed set. Is K globally hyperbolic, which means it is basically seems the same of global hyperbolicity, but with the 2 compact sets. And it is geodesic in the sense that for every couple of points that are causally related, there exists a G geodesic that connects them. So this is the background setting. The main argument of the proof will go by basically approximation of the metrics. So first of all, since our metrics are G1 or G1, or C1 or C11, the curvature quantities are defined distributionally. And we will work with the generalized Ricci tensor, the N-Bakri-Emery-Ricci tensor, where V is a C1 function over M. And the most useful lemma that we used is by graph, which states that there exists smooth Lorentzian matrix G epsilon on M, such that the light cones are narrower with respect they're the ones of G. The G epsilon, the difference between the approximants and the so-called manifold convolution, as introduced by Kunzinger in the previous talk of yesterday, converge to 0 in C infinity lock, and the G epsilon themselves converge to in C1 lock. The main property that we needed was if in addition we assume that the Ricci is bounded by below by K in all time-like directions, then for every compact C and every say nice vector in order to simplify the notations on the tangent space of C, then the Ricci is bounded by below by a slightly worse constant, which is K minus delta. And it can be proven that also the G epsilon metrics that approximate G are globally hyperbolic for every epsilon. So I will annoy you a bit more with the Lorentzian optimal transportation. I will define the set of couplings given to probability measures or the spacetime as the measures on the product with marginals mu and nu. I define also the set of time-like couplings or causal couplings as the ones that give full measure to the time-like pairs or causal pairs of the spacetimes. And then I define, given P between 0 and 1, I define the so-called P Lorentz-Wasserstein distance between them as between two probability measures as the supremum of the P root of the integral of the pth power of the time separation function, and the supremum runs over the causal couplings between them. Maximizer, as in the standard optimal transport theory in a metric space, is called optimal if the maximizers. And as Eckstein-Miller did in their paper, this can be regarded as a sort of Lorentzian distance between probability measures. Now I need a definition for define the synthetic Ricci lower bounds due to Cavalletti-Mondino, which is the time-like p-dualizability, which says that given any two compactly supertotal probability measures, I say that they are just dualizable by a coupling if they admit an optimal coupling, but this coupling is actually concentrated on the set of time-like pairs. So it's a time-like one. I will need to talk also about for defining the lower Ricci bounds, we need also to define what geodesics on the space of probability measures are. So in this setting, basically, geodesics can be reparameterized, say geodesic sigma, such that in a way such that the time separation between any of its points, sigma s sigma t, can be recovered by t minus s times the total time separation distance between the endpoints. And I will denote by R the canonical continuous reparameterization map induced by this fact. Recall always that if G is C11, M is G time-like non-branching, which is a crucial property to prove for the main result. And then a curve in the space of probability measures is, we will call them LGP geodesic, or if there exists a probability measures on the space of geodesics reparameterized in this way, such that the coupling induced, the coupling induced by eta dualizes the endpoints, and the probability and the curve itself is represented by eta. This means that it is the push forward with respect to the evaluation map. The evaluation map is the map that takes a time and gives you the geodesic, the point in the manifold counted by the geodesic at time t. Since in our case, since this is usually called by Lot and Villani dynamic coupling, if you want. Since it is concentrated on this type of geodesics, the same holds for the LGP geodesic themselves, and this is why they are called like that. This is also actually the original definition of LGP geodesics as Mecan defined them. Going on. These are the synthetic Timelike lower Ricci curvature bounds. So I denote by n the weighted volume measure, EV vol G, and I fix k to be any real number and n a greater number than 1 and p any number between 0 and 1. Then we say that our spacetime satisfies the Timelike curvature dimension condition with this parameter, where k is the lower bound on the curvature and n is an upper bounded dimension. If for any couple of compactly supported absolutely continuous probability measures, which are dualizable by a coupling, there exist LP geodesics that connects them, such that for every m prime and t, we have this displacement inequality. So usually the left-hand side is called the Ricci entropy, and this is a way to formulate the synthetic Timelike lower Ricci bounds with this entropy functional instead of the Boltzmann's one that you saw in the talk by Calisti Mondino. And the difference with the classical curvature dimension condition is that first, inside the distortion coefficient tau, there is the time separation function that plays the role of the distance, here we can say, and that depends any number between 0 and 1 for the moment. We say that M satisfies the weaker Timelike measure contraction property with the same coefficients. If you replace the second measure mu1 with a delta on a point which such that the support of the first measure is inside the pest of that point x1, which is an equivalent way to say it. Then the same inequality holds, and since we have a delta for the second measure, the second addendum of the right-hand side, basically, it's not present. I want to remark that this theory of synthetic Ricci bounds has been initiated by McKenny in his paper on the Boltzmann displacement complexity of the Boltzmann's entropy, and by Mondino Sur on their formulation of the Einstein's field equations, then developed in an entropic approach by Cavalletti Mondino and extended by Brown in his recent work. The main result states that if our metric is C1 and we assume the Ricci to be bounded by below by k in all Timelike directions, then we get that Timelike measure contraction property as a curvature dimension condition. And instead, if the metric is C11, then we get, with assuming again the lower bound on the Ricci, then we get the Timelike curvature dimension condition, which is actually stronger. The way to prove this is, employing this approximation argument and using also localization techniques developed by Cavalletti Mondino in their paper, and employing also localization techniques that McKenny used in his paper. Also, why these two results? I want to stress out that the second result follows by the fact that the spacetime is G Timelike non-branching. And we don't know if in the C1 case the TCD holds or not. We just know that it holds for TMCP, which is weaker, but we don't know if the TCD holds for the C1 case. Then the same technique should apply, I think. So why these results are important, there are some sharp geometric inequalities.
Sorry, I have one other question. How does this compare with the talk we heard 2 days ago from the results of talking?
Because they compared the distributional definition of lower Ricci bounds with their synthetic ones, and we did the same, but just only in one direction. We didn't do the from synthetic to distribution basically.
So this is an independent work.
Yeah. So assuming the Ricci to be bounded by below in all time-like directions, the first one is the sharp Broominkowski inequality, which states if we have a two compact Borel GC11, if we have a two compact Borel subsets with with measure bounded by below by this constant capital theta, and if we consider two measures which are the uniform measures on concentrated on AI, then we have this inequality regarding their midpoints, basically, which is the Sharp-Broominkowski inequality. The other geometric consequences are, first of all, we assume now GC1, and in the case, the Sharp-Born-Myers inequality states that in case K is greater than 0, then we have the pi times the square root of n minus 1 over k is an upper bound for the, let's say, the causal diameter, I would say, of the space-time. And the last one is the Sharp-Bishop-Gromov inequality, which states instead that if E is a compact and tau star-shaped subset with respect to a point x in M, which means that tau star-shaped is the same of star-shaped, but you replace the geodesic segments with G geodesic segments to be inside the set E. Then for every positive couple of R and capital R with these bounds, then we have these two inequalities regarding the volume of the ball intersected with E, and regarding the Minkowski content of the same set, basically, where S is say a sine functions, is the sine function with some k and n minus 1 and n minus 1 coefficients. Yeah, it's just sorry. The S is just. No,
not the SKN. The SR.
Yeah. It's sorry. It's the Minkowski content of this set, basically.
It's the derivative.
Yeah. Sorry, my bad. And the last geometric consequences are, first of all, that TCD is sufficient to get n as an upper bound on the Lorentzian house of dimension, as defined by McCann and Seyman. And lastly, that if G is C11, and this is the other case where the non-branching property is crucial in the proof, basically, is that the set of given in two probability measures like that, then the dualizing couplings between them and the set of couplings representing the G geodesic between them, and I will collect them like that, they are singletons. Moreover, they are induced by a map, and we can say basically that the optional transport problem, in the sense of like Monge, we can say it's solvable. There is a transport map that induces the pi. So lastly,
sorry, again, if you assume just C1, but you assume non-branching, that's not enough. Is that right?
yes, yeah. Lastly, okay, as I already said, we have to study the converse implications, so to pass from the synthetic to distributional bounds, as done by Kustinger, Ober, Guggenberger, and Vickers. And the structure, we can say, of these Timelike Ricci spaces This is like defining a nice notion of convergence, we can say. The globalization theorem for the timeline curvature dimensional condition. So what it is this? The timeline curvature dimensional condition as the curvature dimension 1 as a, say, reduced version, which uses a slightly modified distortion coefficients. And under the assumption of non-branching, it is been proven really recently in this impressive paper by Cavaletti-Millman that they are equivalent. But for the TCD, this is not available. The fact that the TCD implies its reduced version just follows from the properties of the distortion coefficients, but the other direction is unknown. And lastly, as already said by Ohanian and also Kutzinger, we lack a Lorentzian version of the Riemannian curvature dimension condition. And this is, to me, unknown, actually, how to do that. Thank everyone for listening me today.